I'm not feeling well. Okay. I'm actually afternoon I was really, really tired and I also took some medicine. So I was like drowsy and I kind of, I don't think I could have taken the class. Right now I'm just like, just too tired, but I can still take the class. Okay. So we'll go ahead. This is some issue that I have to address, right? So there is no redundancy. There is no substitute teacher or redundancy. So what happens if something happens to me, right? That's an issue that I always consider. One is there is always time redundancy. I try to give some buffer or leeways in the schedule, right? We miss a week or something like that, we can always get back. And then it also, my work ethics is such that, you know, flu and all that typically doesn't stop me from, you know, skipping the entire week. Okay, I can somehow show up, and also this is online, so it's not contagious. Like there is really no excuse. I can still. I would like to show up and get the work done. What you have scheduled this week is signals and systems, and I think we'll get that done next 2 hours or 3 hours. Okay. So time redundancy and some sort of like work ethics, right? Those two kind of is what I rely on. Yeah. Okay. So today we are going to look at signals and systems. This is part of the simplified revision series, right? Where we look at gate biomedical PVQs and what is left as signals and systems, and then analog and digital electronics, right? So what makes isn't this important as so if I look at 4 years of question papers, okay, there are about 28 questions. Okay, this is considering also some of the questions from control systems and all that involved in transfer functions that we discussed last class. Okay, so this corresponds to approximately 7 questions every year. Okay, 7 questions per year. Okay, and out of that 7 questions, roughly two are controls, basics of transfer function. Okay, impulse response, no, this response and all that. So I would say there are about 5 questions that are yes and S. And these 5 questions where non-BM students typically get an edge. Okay. Let me also say what typically happens. Out of this, say 5 pure SNS questions, okay, 3 to 4 are answerable in the exam. There are always 1 or 2 questions that are like really, really hard, typically intended to waste your time, unless you're extremely good at signals and systems, right? You're a co-author with, Oppenheimer and Minsky, or at least you have read the Oppenheimer and Minsky start to end, including, all the derivations, right? There are always 1 or 2 questions that are not answerable in the examination. Okay. So there are 3 to 4 questions that are answerable according to me, which IN students, electronic students in the previous years, EE students, they easily get 2 or 3 out of them. Okay. So this is where IN students kind of get an edge. IN, EE, easy. Okay. And what we need to notice is medical students need to know sufficient yes and S, right? So that they don't give any unfair edge, right? So BM students typically have an edge in medical imaging, bioinstrumentation, and all that. So if non-BM students, IM students, and all that somehow manage to spend time and learn those subjects, right? BM students somehow need to learn this subject, okay, which is when the competition gets really, fair and equal. Okay, so that effort has to be put up from BM side. And today, what we'll do is, I will, I will certainly do. There are this 3 to 4 answerable questions every year, right? I'll try to tell you how to answer them with minimal recall, minimal recall and things like that. Okay, this is one subject where there is a laundry list of formulae. Okay, take any transform. There are like, what is a transform? What is the property? Right? There is a very, very big list. Basic transforms, list of transforms, properties of transforms, and you take different transforms. Each of them have a list of transforms and properties of transforms. This list goes on and on and on. Okay, so there is a lot that needs to be recalled. But what I will try to do today is, there are many things you can answer with minimal recall. Okay, bare minimal things, if you recall, at least you can answer 2 to 3 questions. Okay, I will certainly address all of those questions today. Okay, that is the objective. I'm also not doing well. Okay, so I think this is what is reasonable to do today. Okay, at the end of the day, no unfair edge to anyone in the competition, right? That is the objective here. And let's quickly see. We have seen many questions from, this even odd functions you have seen in mathematics. Say, what is a product of even functions, right? Product of even odd functions, sum of even odd functions. So many of these questions we have already seen, that I'm going to skip. Okay, notice there is one more question on even and odd function. We have seen that Laplace transforms. We have already seen that in control systems, Laplace transforms and applications of Laplace transforms, right? Like, okay, in this question, impulse response is this, input a step, what is the output, right, at a specific value. We have seen questions like that. Then some applications of Laplace transforms and all that. Okay, we have seen this. So let's directly go to questions that are mostly SNS. Okay, so this is second order system controls, very hard. I think this is the first question that is somewhat in the SNS system. So I made this thing, right, most important topic for GATE biomedical exams. This is about first order systems, right? Every year there is at least 1 or 2 questions from just that one topic. And it also helps you know some basics of second order systems. Okay. Does anyone know the standard form for a second order low pass filter? Because in this case, some of the things that we need, for example, undamped natural frequency, can be read by comparing with the standard form. So you're expected to recall the standard form for a low pass filter. Of course, the standard form will differ whether it's low pass, high pass, and all that. For a low pass filter, does anyone recall the standard form? Okay, so here a second order filter, low pass filter, is being constructed by cascading two first order low pass filters. Okay, we have 1 by 1 plus j omega by omega 1, and then 1 by 1 plus j omega by omega 2, where the respective 3 dB cutoff frequencies. So if you kind of know the first order system basic terminology, this is kind of like an obvious statement. Okay, if you don't know that, don't worry about it. The undamped natural frequency. First thing is, if you look at cascading, okay, this is convolution in time domain. It's very important. Okay. This corresponds to convolution, one system after another system. Convolution in time domain. If you're looking at functions of time, you have to convolve the two functions, right? In the frequency domain, this will be a product, which is why we typically, one of the primary reasons we kind of always go to the frequency domain, right? This convolution, somewhat of a difficult operator, right? Things become relatively easy if it's in the frequency domain. Product in the frequency domain. What it says is if you have multiple subparts or subsystems cascaded, you can just take the individual transfer functions. You can multiply all of them, right? You can just multiply all of them in the frequency domain. That is, if you have the transfer functions, which is what is given here. So two transfer functions for individual subparts. Now we combine them. The net transfer function is a product. Okay. So let's just this cascaded H cascaded. This will be a product of these two. Okay. You have H1, H2. Okay. And that product corresponds to 1 by 1 plus j omega by omega 1 into 1 by 1 plus j omega by omega 2. Okay. This is the product. And if you write this down, this is going to be 1 by, we have j omega, the square of that by omega 1, omega 2. That is a quadratic term. Then the linear term would be j omega into 1 by omega 1 plus 1 by omega. I'm just multiplying the two things inside the brackets. And the constant would be just 1. So far, I have just multiplied the two functions. At this stage, if you kind of recall what the standard form is, you can quickly answer the question. Does anyone know the standard form? Okay, the standard form here, this is going to be of the form 1 by, okay, notice if there is a plus 1 in the numerator, we can write it this way. Okay, so the constant is plus 1, numerator is plus 1. Okay, and then we have two terms. Okay, there is a linear term. Okay, plus there is a linear term, there is going to be something over here. Okay, and there is a quadratic term, j omega, okay, square by again something over here. So this is the standard form because many of the parameters are defined based on the standard form. You have to recall the standard form. Okay. So what is this first bracket? What is the second bracket? Does anyone know? The first bracket, this is going to be omega n square. Okay. And this is going to be 2 into damping factor by omega n. You could also write this as j omega by omega n whole square. Okay. You could also write it this way. There is a quadratic term. And notice you could actually take the omega n to the numerator. Okay. In that form, this is going to be omega n square. In that form, okay. If you take the omega n to the numerator, what will happen is this: omega n square by j omega whole square plus 2 j omega c omega n plus omega n square. This is also standard form, but I think if you remember it this way, this is fairly easy. You could also kind of try to remember it based on, the Laplace transform. This is in the Fourier version, right? So you could also say there is s square over there, and then there is an s over there, okay? Or you could just give it as j omega. So whatever is the coefficient of in this particular form, let's stick to one. I'm going to stick to this. Okay. The coefficient of j omega is going to be the square of natural frequency. Okay. So in this case, can we answer the question right now? Undamped natural frequency. What they are asking for us in our terminology, they are asking for omega n. Okay. So our omega n is going to be square of omega n. Notice at this stage, omega n square, by recalling it the standard form, is going to be this term, right? Equals omega 1, omega 2. So you know the natural frequency, that is square root of omega 1, omega 2. Notice you could also find out what the damping factor, what the Q factor and all that. At least certainly what the damping factor is, if you can recall the standard form. Okay. And this is for a second order low pass filter. But even if it is not low pass, high pass, the numerator will change. Okay. The denominator is going to be pretty much the same thing. So if you kind of remember the standard form, you can still identify for other filters, you can still identify natural frequency and all that. So it kind of suffices to remember what the numerator is. Again, that is more important. Okay. Now let's get to the next question. The sequences x1, x2 are described as follows. Um, they are given two sequences. They want a convolution. Almost every year there is a convolution. Sometimes it's discrete, sometimes it's continuous. Mostly it's discrete. Okay. So it kind of helps to know the convolution. What I will tell you is I'll show you at least two ways to do the convolution. Two easy ways. Okay. One is, let's write down the signals. Okay, they have kind of set a trap here somehow. Notice your first value is 1 of x1. Okay, for x1, second value is 2, third value is 1. But for x2, be careful, the first value is 1, third value is 2, first value, the second value, that is x2 of 1 is 1. Okay, be careful. These are different. Okay, be careful about it. So let's quickly write down what the signals are. You have x1, the sequence here. We have 1, 2, 1. And then we have x2. This sequence is 1. If you write it as 2, 1, again, that's a mistake. That's a trap that they have kind of set. Okay. But you're right, this is the second value is 1. and the third value happens to be 2. So I have the 0th index, first index, second index, 0th index, first index, second index. Again, let me not get into any complications for the index and all that. So convolution, this is like analogy, yes. One signal is like you upload a, say, post to Instagram, okay? On the first day, you get 10 likes. Second day, you get 20 likes. Third day, you get like 10 likes. On the fourth day, people forget about it. It goes into oblivion, right? Now, you upload one more pic on the second day. What will be the total number of likes, right? The mathematical operation corresponding to that is convolution. For the first pic, you got 111. For the second pic, and also the picture quality also matters, right? For the second signal, this is like quality. This is like the likes that you get upon uploading something to social media, right? So the quality is twice. The likes are, let's say things are linear. Likes are twice. Okay. So first day, what do you get as 1, 2, 1, 1, 2, 1. Second day, you upload a similar pic. You're going to get, again, I need little more space here. So let me write this carefully. 1 second. Yeah, I need. So first day you upload, you're going to get this 1, 2, 1. Second day you upload, okay, what you're going to get is it's a similar pic, so similar likes for that pic 1, 2, 1 on subsequent days. Third day you upload a pic that is twice or a post that is twice better. So the likes that you're going to get is 2 times 1, 2 times 1, 2 times 2, that is 4, 2 times 1, that is 2. What you want is the total number of likes per day, right? So notice on the first day, you're going to get 1 like. Second day, you're going to get 3 likes. Fourth day, you're going to get, or third day, you're going to get 5 likes. Fifth day, 5 likes. Then you're going to get 2 likes. This is the total likes. Okay. So take the sequence, first sequence, multiply it by whatever coefficient you have that, multiply that, and make sure you always give a time lag. Okay, these are like pics uploaded in the different days. So this way you could do it. Let me also write down the indices. So you have the 0th index, you have the first index. The indexes start from 0. Okay, this is like not MATLAB, this is like Python. So this is 3 and this is 4. What they want us is x of 2 equals x of 3. You can see that x of 2, this value equals, value at second index equals value at third index. So that is correct. Okay. I just compared this value and this value. Is x of 1 the first value 2? No, that's not correct. What is the fourth value? That is 2, that is not 3. What is the x of 2? That happens to be 5. This is also correct. X of 2 happens to be 5. Question number 1. So the way that I did convolution, if they give you a similar sequence, they don't give you like a long sequence. If they give you something like short sequences like this, can you take convolution this way? And if you have questions, let me know quickly. Is this doable? At least tell me that. Convolving two discrete signals, two sequences. Nope. Okay, so there is a question on what is this 242, that part. Okay, let me kind of illustrate that. See, on the third day, the indices, on the day kind of differ by one. Okay, one is Python, one is MATLAB. Okay, the indices. So the third value here is two. That is, you are uploading a pic that is two times better. The likes for that will be two times one because it's a two times better pic. Okay, two times two. Okay, the first likes on the first day times the weighing factor, how strength factor, and then you have 2 times 2 for the second day, and then 2 times 1 on the third day, which is what I wrote down as 2, 4, 2. Okay, so this became 2, 4, 2, 2, 4, 2. And each day I just added the number of likes. When I said it in factors of 10 likes, 20 likes. You have like I have written 1, 2, 1 and all that. I didn't write 10, 20, 10. Okay. So, sir, can the strength be negative? Can I put a post that my friends dislike? Yes, that's also possible. If the sign is negative, for example, okay, you're going to get dislikes. Let's say minus 2 dislikes, minus 4 dislikes, minus 2 dislikes. And again, you can keep track of total number of likes. Okay. But right now, things are all positive. You don't have to worry about it. Even that works. Does a 2 for 2 part make sense? So, this is things are I'm writing things, one line has a lag. Okay, there is a lag of one from the previous line. That is, so this is x of one into one. Okay, this is shifted. That is, I move it by one, x of one into again one, and this is also shifted. One more additional shift. This is x of one into two. That is what you have in the third thing. Okay, this is one way to do convolution. I like this way because the analogy is fairly easy. Sir, no, sir. Uh, can we? I don't even want to think about the analogy, right? I don't care what convolution is. I don't like what the analogies. Can I answer that question? You can also do this in a different way. Okay. So you have x1 as 1, 2, 1. Okay. And then you have x2. This is 1, 1, 2. I suppose that's correct. Okay. You can do a quick, you know, table. Many of you have done this, starting with, orbitals and chemistry, all that. We are used to doing this. So this method would also work. So take the first signal, put it here. Okay. 1, 2, 1. Take the second signal, write it down over here. 1, 2, 1. Okay. So the first row, x1 is over here, right? Take x1, multiply by the coefficient factor. What I'm going to get is 1, 2, 1. If I take x1 multiply by 1, that is this number, I get 1, 2, 1. If I take x1, if I multiply by this number, what I'm going to get is 2, 4, 2. If I take x1, if I multiply by this number, I'm going to get 1, 2, 1. Right. Forget likes, forget analogy, all of those things. That's what I got. The actual convolution, you can read it in this order. Is a summation of values across this, inside these lines. So sequence of convolution For example, your x1 convolved with x2, okay, that sequence is going to be 1, the first value. The second value is going to be 2 plus 2, okay, 2 plus 2. Third value is going to be 1 plus 4 plus 1. The next value is going to be 2 plus 2. Last value is going to be 1. You could also do it this way. Forget the analogy, just it becomes a mechanical algorithm, right? Simple thing that you can read. What I have done is I have added things along this, inside this line. I have added this, I have added this, I have added this. There is only one element there. Okay, here is an alternative. And then you have the indices, the line numbers of the indices. Line numbers start from 1. Okay, so this is, you have the 0th index, first index, second index, third index, fourth index. Notice it. So the convolution second index corresponds to 5. I have 2, 4, 2. Yeah, I didn't write the x2 here. I just wrote the x1 here. Okay, so I'll have to redo this. The x2 is going to be, it's not 1, 2, 1. Okay, as given on the question. This is 1, 1, 2. Okay, let's also get rid of all of these things. So I take x1, I multiply by 1. That would be again 1, 2, 1. Just take x1, multiply by this strength or this coefficient. For the third row, take 2 and multiply by x1. So 2 times this row, right? This row, 1, 2, 1. If you take that, you're going to get 2 times 1 is 2, 2 times 2 is 4, and then 2 times 1 is 2. Again, you can read the convolution as sums across, across these diagonals. So the first value is 1. The second value is 1 plus 2. Okay. Third value is 1 plus 2 plus 2. This diagonal. Okay. That is 1 plus 2 plus 2. That is 5. Okay. And this is a 4 plus 1. The last value is 2. Yeah, I just wrote down this incorrectly. Okay. I didn't write x2 there. I again wrote down x1. So you could also do it this way. Notice now you got your convolution. This number happens to be the convolved at second index, that is 5, third index, that is 5, right? You can still go back and get that. This is what we got, I suppose. Second index, it's 5, third index, it's 5, last is 2, then you have 1 and 3, right? Yeah, you have 1, 3, 5, 5, 2. So these two values are simple, and then x of 2 happens to be 5, x of 2 or x of 5. Okay, so pick your method. You're doing the same process. Essentially, convolution involves the definition involves a shift. Okay, how you do the shift? Your shortcut to do the shift is this, whatever method that I am suggesting. You could do it whichever way you want. Okay, this is the second method 2. Here's almost every year there is a question. We'll go to the next one. Yeah, there is one more convolution question. This is 2023. This question is 2021. So now instead of giving the sequence, they have given the sequence in a figure, right? You can technically write down the values from the figure, but some of these are, the scale of the this axis, h axis and y axis is not known, but the x axis, the values are marked. You know the scale there. You can write down the sequence. So your xn, your xn, the sequence is going to be first value is 0, second value is 0.1. I'm reading here. Okay. Third value is 0.5. Fourth value is 0.4. There are only four values. Indices start from 0. Okay. The first value, second value, third value, fourth value. Indices start from 0, 1, 2, 3. This is your x of n. What is given in that question as your y of 2 is 1. So this value is given to be 1. Y of 3 is 0. This is 0. And technically even y of 0 is also shown to be 0. They are asking you for what is h of 0. Hey, what is this value? If by convolving these two signals, you get the third signal shown as a figure, like, what is this signal? What is h of 0? You just need this one value. You don't need the entire value. In fact, there are only two non-zero values. Okay. So let's write down our h of n. This happens to be the first value. We don't know. Let me write it as h naught. Second value is non-zero. Let's write it as h1. Third value, fourth value are 0. H of 2 is 0, H of 3 is 0. These two are unknowns. In fact, what you're trying to find is what is H naught. That is what you're trying to find. Let's also write what is Y of n. This happens to be first value is 0 here. Okay. Second value is, we don't know. Let's write it as Y1. Okay. And then third value is given to be 1. And a fourth value is given to be 0. And then when you convolve things, this is the convolution can kind of increase the length, okay, by definition. So the last value we have y4, which need not be 0. The lengths of these sequences need not be the same, especially the one that you get after convolution. So far, this is all I have written down as the information given as a sequence. I haven't done anything, I haven't done anything complicated. And what we want is, hey, what is this value? What is this h naught? We are trying to find this. We don't care what is y1. We don't care what is y4 and all that. So y1 by definition is the convolution. Ym is this convolution. Again, we can easily find it out. How do you do find out? Let's write down the first sequence, the x1 here, 0, 0 0.1, 0 0.5, 0 0.4. Let's write down the coefficients in this side. Okay. The first coefficient, this is h naught, h1, and we have a 0, 0. So take this row, multiply by these coefficients. take the row, multiply by h naught, that you're going to get 0 times h naught, 0.1 h naught, 0.5 h naught, 0.4 h naught. I took that row, multiply by this coefficient h naught. I've just written the sequence in order: h naught, h1, 0, 0. At this stage, I know this is 0, this is 0, this is 0, this is 0. Take that row, multiply by 0, you're going to get a 0. This is 0, this is 0, this is 0, this is 0. H1, again, you are going to get a similar thing. That happens to be 0, 0.1 times H1, 0.5 times H1, 0.4 times H1. You can read the convolution from this table. How do you read it? Summation of diagonals along this line. And you have to be careful where it starts, where it ends, right? Yeah. I'm specifically going to read for things that are known. Shall we read y1 is an unknown, okay? So y of 0 happens to be this value, that is 0. There isn't any 0 equals 0. There isn't any information there. So I'll skip that. Y of 1 is an unknown that happens to be this summation. Y of 1 is an unknown, so that summation again is not useful. The two useful bits are the next two diagonals. We know the value of y of 2, we know the value of y of 3. Okay? So we know what y of 2 and y of 3 are. So notice y of 2, this value, it's a third value, has an index of 2. That happens to be this summation. 0.1 h1 plus 0.5 h naught. And then y of 3 happens to be this summation. In fact, that happens to be 0. Y of 3 is 0. That happens to be 0.4 h1. Sorry, 0.5 h1 plus 0.4 h naught. H naught. Two equations, two unknowns, you can solve for it. Also, we know the y of 2 value, right? That happens to be 1. So I'm also going to write it down from here. Two equations, two unknowns, you can easily solve for it. What you want is the value of h naught. This is fairly doable. So, if we solve these two equations, we get the answer. So I'm going ahead and doing this. Okay. This is not a question that I would skip. Perhaps I would skip it in the first pass. But in the second half of the exam, after 2 hours, 2.5 hours, this is one of the questions that I will certainly try to solve. Okay. So the Rose equation says your H1 happens to be minus 0.4 H naught by 0.5. Okay. Then you can substitute that for H1. So your 1 equals 0.1 into this Rose term H1, that is minus 0.4 by 0.5 into H naught. Okay, that's your H1, and then you have 0.5 H naught. You can easily read out what the value of H naught is. That happens to be by this number. Okay, 0.4 divided by 0.5 into 0.1, that is 0.08. So you have 0.5 minus 0.08. 0.42. 1 divided 0.42 happens to be 2.38. It's going back to our question. So this is, we just found out our H naught to be this. Only thing is, notice there is again a question from discrete convolution. Okay. I use a table method. Table method or even this method, either should work. Okay. More than one and the same. Okay. I use a table method. Only thing is, information now is given in sort of a figure, right? In a somewhat of an obfuscated format, right? And this is typical of GATE exam, right? Simple things they try to give it in a roundabout way, right? But we read that, and once we read that, this is fairly easy. There are two unknowns you have to solve for this unknown. Okay, so that is with convolution. Notice. So at this stage itself, there are lots of question. The table method or the likes method, right? Which is why there is also, if they either ask convolution or they ask cross correlation. Cross correlation, you have to do one more change, but again, you can get it from the table method with a change. Small modification, you can get cross correlation, but I don't want to confuse you at this stage. So I kind of put that question towards it. So bottom line, if you know how to do convolution, you also know how to do correlation, cross correlation. Okay, but we'll come back to that towards the end. Okay, continuous signal x of t is described by. Now, this is continuous convolution. You can answer this if you can do some basic scaling, mirroring, shifting, and all that of signals. If you know how x of t looks, if you can know how to shift it, x of t minus a, t plus a, if you know how to do with that, you know how to mirror it, x of minus t, how does that look, and how to shift that, you can easily do this. Okay. Else, this is one of the questions that I would kind of skip. Okay. Continuous convolution. You cannot put a simple table and get this. Okay. Typically. But in this case, xt convolved with itself. Okay, let's write down what this convolution is. X1 convolved with X2 in case of this continuous time, let's say. X1 convolved with X2. This is a function of time. That whole thing is a function of time. Okay. That happens to be minus infinity to infinity. X of tau, the way I write it, okay. X1 of tau, X2 of t minus tau, t tau. We kind of remember it. Notice this tau and this tau, roughly the things inside the bracket, the tau's cancel. Only it's a function of time, right? Only is a function of time. Okay. So only t survives. It's a simple mnemonic. Roughly tau plus t minus tau. Okay. You get t, right? The things inside the bracket gets cancelled. Okay. You could also write it as x2, take x2, convolve with, this is kind of symmetric. You could also write it this way. Okay. So that doesn't matter. In the discrete case, this integral will become a summation. Okay? And for most gate purposes, what you need to know is, again, if I have to repeat it, notice x1, this is a function of time. Okay. In the frequency domain, you have x1 of s, the product of two functions. We already made use of this. This is a convolution in the time domain. This is a product in the frequency domain. You need to know at least this much. Okay. With that, so if you can do this, how does this function look and all that? It's actually a function of tau minus tau. Then you can easily do convolution. Okay. In this case, all you want to know is whether the convolution, notice convolution, this is an integral. It's in the integral, it's a product of two terms. If one of the terms is zero, the integral is zero. In a certain region, certain range, if the one of the terms is zero, the integral is zero. So you can exploit that and find convolutions very easily. So I'm going to say that, okay. Let's have a common t equals 0. This is time axis. This is time axis. This is again time axis. This time axis. T, 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 T. In fact, T, we can, we are going to deal with tau. So this is all tau. Tau, 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 tau. First, what I'm going to put is x1 of tau. That's fairly easy. It's 1 between 0 to 1. Everywhere else, it's a 0. So the first function is this. The first function. It is 1 between 0 and 1. Everywhere else, it's a 0. This is going to be 1 of minus tau. Why am I looking at it? Because the integral has this t minus tau. When t is 0, this is x2 of minus tau. That function looks like this. Okay. And this is case where t equals 0. If you can somehow write two functions where t less than 0, t greater than 0, if you can draw these two functions, you can technically answer this question. If you have trouble drawing that, then there is going to be trouble answering this. For negative t, this reverse function is going to move towards left. Okay. So that will look something like this. You can use Desmos and quickly try it. This is going to be, for negative values of t, this is going to move that way. This is your x1 of t minus tau. Take that function, shift it. But the shifting, you have to do it this way, okay? This is t minus tau. Or you can also read it as minus tau plus t. If the shift is negative, it's going to move towards your left. If the shift is positive, it will move towards your right. So the function kind of, the positive shift, it kind of starts looking like this. In fact, with the positive shift, it will be, yeah, for positive shift, it will look like this. This function is x of minus tau, again plus t, but this t is positive. For positive, this function is going to move towards your right. Why that is the case? The simplest thing is, take this moves, plot any function, see how it moves with the delay that you give. In fact, I have done this in some of the recorded videos. Okay. Okay. So the domain of interest is this 0 to 1. This is where the one of the functions is non-zero. If any one function is no, 0, product is 0. Notice one function is 0 for t less than 0. So the product is 0. This is correct. We want all the true statements. This is correct. The product, the integral involves two products. One of the terms is 0 for t less than 0 in this range, in a specific range minus infinity to infinity. In that till t equals 0, one of the terms is 0. Okay, so the product is 0. T greater than 1, this thing wouldn't have fully completely moved. Okay, the width of this is 1. The width of this is 1. Okay, so it's not 0 even for t greater than 1. Technically, I need a little more space, and I also need to draw that if I have to convince you that. But certainly, this function would have certainly crossed this milestone for t greater than 3. It would have shifted by a lot for this value. Okay, slightly harder to see, but it's shifting towards the right. If t value is very large, let's say 3, it would have completely moved out of this range of interest. Again, one of the functions is 0. So this is also correct. And the third range given here is 0.1 to 0.75. Okay. You can actually get a non-zero function here. In fact, if you take two constants, if you integrate it, you are going to get a straight line. For that reason, the slope also will not be 0. This is slightly harder to see. Okay. But P is also correct. That is slightly harder to see at that stage. In fact, how the convolution should look in this case, let me also draw that. The convolution should look like this. If you actually do the integral, convolution will look this way. Okay. Constant and constant, you integrated, you get a straight line. So technically the slope from 0.1 to 0.75, that's a non-zero slope. If you integrate it, you get a non-zero value. Okay, as I said, this is fairly easy if we can shift functions at least on paper, if not in your mind. Yes, this is a very hard thing to do. Okay, continuous convolution is something that I would consider avoiding if you have trouble with this. The definition is fairly simple, and at least answer these questions. In fact, notice. So if you kind of look at that relation over here, there is one band limited signal with a band of this non-zero values. There is another band limited signal with a band of this. Let's say this is X1, this is X2. Okay, this is a band of that. This is typically lesser than this. The convolved spectrum will look like X1, X2. Okay, looking at the Fourier thing, let's put a capital thing. I'm looking at the spectrum. This is X1, spectrum of signal 1, X2, or Fourier transform, frequency domain. I'm looking at the function in the frequency domain. Notice if there is any range where one of the functions is 0, the product is going to be a 0. So this function will be band limited. Whatever this shape is, the product, that doesn't matter, but it ends here in this range where one of the functions is 0. This is, the product is 0. So if you convolve two band limited function, the resulting function will have a lesser band, or the band, the smaller band determines the uh, band limit of the convolved signal. Okay, let's say this is 400, just throwing some numbers. This is 400 kilohertz. Okay, this is 200 kilohertz. The convolved signal will have a band limit of 200 kilohertz. This is something that directly shows up from this property. Convolution is a product in the frequency domain. And if one of the terms is 0, the product is 0. You can easily see how that works for band limited functions. Okay. So again, this is a very, very typical question for the concept of interest. I'm just pointing that one out. It's fairly easy to see. In fact, much easier than what happens with this shifted products. Okay. Okay. Quick note on that, but let's get to this question. So the takeaway point here, this is limited by smaller band. Limited by smaller band. If one of them is 0, the product is 0. Okay. Okay, I said that as an aside, and now if you come back to this question, okay, this is an aside remark, okay? You don't have to. It's a side remark for a different question. If you come back to this PVQ, analog signal is sampled at 100 megahertz to generate 1024 samples. Only the samples are used to evaluate again 1024 samples, 1024.50. Separation between adjacent frequency points is. I'm going to presume what this sampling and all that. I'm not going to explain that, okay? But if you have a continuous signal, again, if your signal is this, let's say band limited signal, simple triangle signal. Okay. In fact, I can kind of use the next page also to have space. This is in frequency, hertz, megahertz. Okay. If your original signal, spectrum of your original signal Okay. X of t. Take Fourier transform of that, x of omega. The original signal is band limited, that is, there is a specific spectrum is non-zero only for a certain values. Okay, beyond the frequency, beyond IF naught, there is a bandwidth, things are zero. Okay. Now you can take the discrete, that is, you can sample the sample x of t. This is a discrete signal. If you look at the spectrum of that, spectrum is going to repeat. It repeats. Same shape repeats. If you have a heart there, a nonlinear thing, let's say whatever shape, it kind of repeats. One of the questions is, what is the distance between this repetition? That is, if you take this point and if you take this point, how far away are those things? If you know the sampling frequency, you also know this distance. In fact, this distance happens to be the sampling frequency. Okay. Your Fs by definition is 1 by time period. This is the relation between length of a heartbeat and heart rate, right? Time period and frequency. If you know the sampling period or sampling frequency, you know the distance, how far away these things are. Okay. So, which is what is given in this question. Your Fs 100 megahertz. So repetition is going to be in the thing frequency domain. Things are going to be at a distance of, the repetition is going to happen at 100 megahertz. Okay. F of t. This is sparse Fourier transform, but the discrete version. That is, if you were to sample this, if you were to sample this, the spectrum can be continuous, but if you sample, what do you get? Right? A quick way to do that algorithm for that is F of t, but you're discretizing the spectrum. You're only taking samples, at evenly spaced points. How far apart are 2 points? This is, let's say, delta F, which is what they want in that question. So total is Fs. You have 1024 points. This is fairly easy. Okay. Your delta F Fs by number of points. In this case, this happens to be 100 into 10 power 6, that is megahertz. By number of points, you have 24 points. What is the answer here? I think your answers are in kilohertz. So in fact, you can write this. Let's write this in kilohertz. How much is this? 97 point something, right? Suppose the answer is B. So in this case, now there are 1024 points here. Total separation distance is 100 megahertz. So far, I haven't said anything complicated. Things are, I suppose, still, fairly on the ground level. And when you are also looking at if there is a convolution of two signals, two band limited signals, the convol signal is band limited by the smaller band. That also we can easily see, and often a target of interest. The third thing here is, hey, in this case, let's say the separation happened to be 100 megahertz. What if we sample it at a lower rate? Okay, quick pointer at a lower rate. Let's say I do it at 25 megahertz or something like that. The separation, it's say, let's say this is, let's say this is 30, 30 megahertz. Okay, the band limit. I'm just giving some numbers. So 30 ends here, 50 is halfway between the two peaks. The next peak is at 100. But for some reason, by mistake, I sampled it at 30. Let's say I sampled it at 50. The distance between them is going to be 50. I'm going to get a repetition like this, where there is overlap of spectrum. This is like, a class where student is speaking, teacher is speaking. Yeah, the technical term for this is aliasing. Okay. But there is, under classical conditions, you cannot really eh, get back the signal. Okay. This is, the signal is mixed. Now the soundbar is made. Hard to separate that into water, salt, whatever, salt, whatever you put, masala and all that. You cannot separate things out. Okay. This is not like a salad where you can still pick things out. No, this has kind of become like a sambar where you cannot separate individual frequency components. Okay. So just with the repetition idea, I said you can also see the third most important concept, that is the Nyquist sampling rate. To avoid this is called aliasing. This is aliasing, interference, where we cannot get back the signal. So for this interference, so to avoid aliasing, to avoid this, you need to at least do your FS should be greater than twice the bandwidth. Bandwidth is 30, you should at least sample it at 60. 70, 80, 90, 100 is fine. But if you are less than twice the bandwidth, for example, if you are 50 megahertz, there is aliasing. This is one important condition that we cannot afford to not discuss. So I put it up here. This shows up in medical imaging, signals and systems, and we cannot get away from this. Actually, this is the classical sense. You can get away from it from the in the modern sense. Okay. Um, so this goes by the name Nyquist. Nyquist, right? Okay. Because we're discussing the spectrums and some properties of spectrums, I kind of put that over here. In fact, if you look at this question, if you look at this question, 8-bit successive approximation of ADC converter. Okay, ADC has a clock frequency of 1 megahertz. Assume that the start conversion and end conversion signals occupy one clock cycle among the following options. What is the maximum frequency that this ADC can sample without aliasing? Fairly simple. This is your, your now your working frequency is like your working rate is digitized. This is at 1 megahertz, right? It cannot go smaller than that. Clock frequency puts a lower limit on that. If there is just one bit, based on our discussions, your sampling should be greater than, or to avoid aliasing, okay? Let's say there is just, one bit of information in each sample. Your Nyquist 0.5 of that, 0.5 megahertz. There is just like one bit of information. But instead of one bit of information, you have 8 bit. You have 8 bits of information. On top of that, you also know need a there is some latency involved. You need to spend one bit, one clock cycle at the start and end to say when it starts, when it ends. So totally you need 2 plus 8 bits. If it is one bit, you can do it fast at 0.5 megahertz. Okay. But now you have like 10 bits. How fast can you do that? Right? You, of course, you're going to, this is 10 bits are going to slow down things. 10 bits. This corresponds to take that 0.5 megahertz. Things are going to be much slower. How much slower? 0.5 megahertz by 10. How much does this correspond to? So in simple English, 10 bits instead of one baggage, you have like 10 bags, right? Things are slower. This is, the approximation involves, signal is 8 bits. Then it says, you start and end also, you need to allocate one clock cycle. The start and end, there is some latency there. Just the signal, 8 bits. But the algorithm, where does the signal start, where does the signal end? To identify the signal, there is some latency involved. That is, one bit in the front and one bit in the end. Okay. That comes from the question. Assume that, start, when does it start, when does it end, takes one clock cycle. So I put that. There is some extra latency involved. So I put that added on. The question says, indirectly says, hey, this is not this technically 10 bits. If you have to consider not just uh, not just approximating it, but also like at the end of the day, you want to identify it. So you're also going to use some bits, the front and back. Okay, so this is notice. Things are, why did I divide by 10? Things are going to be slower with more bits. Things are slower. So instead of 0.5, you can only do things much slower than that. And that corresponds to, I suppose, this number is 50 kilohertz. Okay. So anything less than that is fine. Your option C is slightly lesser than that. You are still okay. If your information tries to go, above this, you are running into issues. Okay. So notice, two questions. What is the separation distance? Is fairly easy. Nyquist, some question on Nyquist. If you understand the question, this is also fairly easy. Okay. The worst case scenario, even if you were to put a 8 here, let's say you put an 8 here, what you're going to get is 500 by 8. Okay. Even then, 99 won't be smaller than that. Only 49 would work. Okay. Even if you put an 8, your option as answer is still C. Okay. Things are slower than that maximum rate. So you're not penalized for any complications here, but still. Okay. So there's a question on Nyquist. And then there is this question. Now, here is the font is too small. Let me read it. X of t is a real continuous time signal whose magnitude frequency response is shown below. After sampling x of t at 100 radians per second, your fs is given. Your fs, this is 100 rads per second. This is in omega. Okay. Actually, technically, this is your omega s. Rads per second. What is this omega and rad? We have seen this, right? If your omega is 2 pi nu, f is in hertz. If you multiply by radians, you'll get radians per second. That is omega. So what is given is omega, not f. Okay. And after sampling x of t at 100 radians per second, spectral point P is down converted to. Now, your signal has somewhat of interesting spectrum or a cooked up spectrum. There is signal that is band limited till 50, and there is one spike arbitrarily at, if you had to write that number, this is 150 plus 12.5, that is 162.5 rads per second. There is a spike. And you are sampling it at 100. So obviously, in this case, your signal is going beyond the sampling range, right? So there is going to be aliasing. Okay. This will get aliased. There is going to be aliasing. There is going to be aliasing. That is, it will be confused with the smaller, signal within the band. That is, it will be confused. It will be confused. That is what they mean by down converted. You're going to confuse with one of the smaller signals. The way to do it, this is fairly simple. Which smaller signal will you confuse it with? So in the sample thing, that will show up somewhere here. Okay, somewhere over here. It will show up. The bigger signal will be confused here with the smaller signal because of aliasing. So how will you find it? Unfortunately, to make things easy, they have given you the modulus. You're looking at the absolute value of the spectrum. The sign is not important. Okay. This is fairly easy. You have to draw this. You have to draw these repeated peaks that are touching. They are touching at Fs or omega s, whichever the units of x-axis is. In this case, it's omega s. Okay, what I have here is this axis is omega. Okay, in fact, what I have on the x-axis is specifically omega of the input. Let's also give it some colors. What I have here is omega of the input. This is the input frequency. What I have here in the y-axis is omega of the output. And these have slopes of 1. These are nice slopes of 1 and minus 1. These are nice straight lines. Okay. This has a slope of 1. This has a slope of 1. Even this has a slope of. This is a negative slope. This is a slope of minus 1 and all that. So this is a straight line. What it says is till omega s by 2. Okay. Your input frequency is same as the output frequency. The slope is 1. This is a straight line. X equal to y equal to x line. Whatever is the input, that will be your output. But there will be confusion if you go beyond the Nyquist rate. That is beyond half the sampling frequency. So there will be confusion here, there will be confusion here, there will be confusion there also. Okay. So any point, give me an input, I know what the output is. That is the figure that I have drawn. So the input frequency of interest here is, notice, let's also give actual numbers corresponding to what is given in the question. Okay. Let's also give actual numbers. You're sampling at 100. So this is at 50. Your input of interest is at 162.5 rads per second. So this is 150. Okay. This is what you want. 162.5. Where will that go? That kind of goes here and touches this value. And notice the maximum value is going to be WS by 2, that is 50. Can you find out what this value is? This is straight line. So till from 100 to 150, whatever this value is, if it's 120, it goes back to 20. If it is 130, it goes to 30. If it's 140, it goes to 40. If it's 150, it goes to 50. If it is 155, it decreases. If it increases by 5 from 50, it decreases by 5. If it increases by 12.5, it decreases by 12.5. So your answer in this case is 50 decreases by 12.5. That is 37.5. Let me pause. This is the relation between input and output. I have given it in a graphical format. The slopes are all 1, plus or minus 1. So given any input value, you can find the output value, which is what I did. Did you follow that? You want me to repeat once? I'll do that again. Fairly easy, right? So notice, let's write down. So this number 150, this is going to go to 150. If it, let's say this is 125, this will be going to between 0 to 50, right? So 150 will go to 50, and then 125 will go to half of 50, that is 25. Okay. In the side, it will start decreasing from 50. In this side, it starts increasing from 0. It will increase till 50. So 100 plus 5 increases by, the value is 5, output is 5, right? 100 plus 50, value is 150, increases 50. That will be the output. 162.5, right? It will start decreasing from 150. So at 150, it's at 50, decreases by 12.5. So in the absolute case, this is, if you're looking the absolute value of the spectrum, this input output relation is fairly simple. This repeated peaks. That's something that you have to recall. Other things you can fill up. So in fact, what I was, so this height, if you notice, this height, that height corresponds to a decrease of 50 from, 12.5 from 50, that happens to be 37.5. The output is going to be 37.5 radians per second. Okay, one more question from the spectrum. X of s is band limited, continuous time x of t. The spectrum is known as band limited. It's zero beyond 200 hertz. Only less than 200 hertz, it's non-zero. Okay, this is also a straight line. I can see this is a straight line. So in this range, it's a line. It is not an increasing line, it's a decreasing line that I can fairly easily draw. Signal is uniformly sampled at, now there is a sampling frequency involved, that is at 600 hertz. Now we are looking at the Fourier transform of the sample signal, x s of f, sampled Fourier transform. Value of, the spectrum value at 600 by 500. So this is where again, if you go back to what I said, they are asking you the same question from this. You take any spectrum, if you sample it, it's going to repeat. How far away will it repeat? Repetition distance will be the sampling frequency, Fs, right? So let's, the same concept, let's again repeat it. Now let's draw that, okay? They're looking at only positive values of F. So I get some little more room here. This is mod F. Give me 1 second. Initial signal is there band limited at 200. You are sampling, this is at 200. You are sampling it at, this is in hertz. It's not in radians, and you are sampling it at 600. So there is 400 over here, and then there is 600 over here. This is what you're sampling it. So there is no aliasing. You don't have to worry about it. This is decreasing line that is decreasing. Line that is a line that is decreasing. You could also see that what is the starting value? X of 0 happens to be 0. It starts from this. X of 0 happens to be 0. If you put f is 0, this is, sorry, f of x of 0 is 1. Starts from 1, decreases from there. We could also see that x of 200, if you put f is 200, you get 1 minus 200 by 200, that is 1 minus 200 by 200, that is 0. So it starts at 1, ends at 0. And it's a decreasing straight line, I draw it. This is the original spectrum. The sample spectrum will repeat. So this is, let's get some marks here. This is 400. So this is 600 minus 200. And then this is 600 plus 200. This is at 800. So the sampling thing is going to repeat. How far away apart they will repeat? It's fairly simple. They will repeat at 600. And so on. Okay. In fact, this is your x of f. This is your x. Yes, so that is your x of f original spectrum. Your repeated spectrum is going to look like this. Your repeated thing, this is x sampled spectrum. This is repeat. Now what they want is fairly simple. Hey, what is the sample spectrum? What is x value at 600? We know that to be 1, right? It starts at 1. What is the value at 500? What is this value? Can someone fill up this value at 500? What would be the value? We know the value at 600. This is, the original peak repeats. So this value is at 1. This is at 1. How much is this? Anyone? 0.5. Yeah, notice, in fact, this is actually midway between 400 and 600. To actually draw it correctly, that's correct. Notice this is at, this goes at 0, right? This is at 0, this is at 1. Midway between that, this value is going to be 0.5. So what is the ratio of those two values? Yeah, you get your answer, of course, is just, take 1, divide that by 0.5. This is your x of the sample x at 600 by sample value at 500. This is 1 by 0.5. That happens to be 2. 2.0. Okay. Let's avoid any clutter and now avoid any aliasing. So this is in hertz. Okay. I think we are halfway down the line, right? So yeah, let's finish it. Okay. Let's do at least the easy moderate ones. Okay, now we go back to the next question. So notice, see, there is every year, we discuss 4 questions from the spectrum. Almost every year there is a question from the spectrum. So whatever I discussed, okay, if you ask me, it's moderate. It's not too complicated. At least I try to like say make it as simple as possible with as little mathematics as possible. If you at least know this much, you can easily get 2 marks. Okay. Okay. Now FIR, finite impulse response filter has only 2 non-zero samples in that impulse response H of n. H of 0 is this. Okay, two values are non-zero, 1 and 1. Discrete time Fourier transform of H of n equals H e power j omega. Okay, what they want is as a function of a normalized angular frequency. Okay, the range. What is modulus of that? So what is given here is H of n. This is discrete. This is just 1 and 1. We want to plot it as a figure. So that 0 you have a 1 and at 1 you have a 1 and then rest of the values are 0. Negative indices are all 0. This is your H of n. Okay, now we need the definition of this. What is H of E j omega? This is a summation. I suppose this is infinite summation. H of n e power minus j omega n. This by definition is a DTFT. So you are trying to write the original signal as summation of complex exponentials, weighted complex exponential, right? That's one way to look at it. Instead of a summation of, let's say, sinusoids, sines and cosines, right? You're trying to write it as, in fact, a complex exponential. And your limits, of course, is n varies from minus infinity to infinity. In this term, there are only 2 non-zero values of n. This is your n, of course. What you have written here is n. Notice all the negative values is 0. H of n is 0. The positive values, above 2, 2 and above, this is all 0. So there are only 2 non-zero values. And both of them happen to be 1. Right? So the summation is fairly simple in this case. Okay, the summation happens to be H of 0, that is 1. If you want clarity, let me also write it. H of 0 into e power minus j times 0 plus H of 1 e power minus j omega into 1. There is j omega into 0. So this term goes to 1. E power 0 is 1. And this term is just e power j omega. So what they have given is, so notice this H of e power j omega happens to be H naught, that is 1, plus H1, that is 1, e power minus j omega. All they are asking you for is, hey, can you find the absolute value of this? Okay, this happens to be 1 plus cos omega minus j sine omega. The absolute value of this, that happens to be square root of the real part square plus imaginary part square. Okay, 1 plus cos omega square plus sine omega square. This will simplify, and can you tell me what the simplified result will be? Okay, let me write down one more thing. So this is going to be 1 plus cos omega square plus 2 cos omega plus sine omega square. Okay. This is some elementary trigonometry, so my font is not good. Okay, but it's fairly basic trigonometry. Cos omega square plus sine omega square is 1. So you have 2 plus 2 cos omega. Can you simplify that? Square root of 2 plus 2 cos omega. This happens to be square root of 2 plus 2 cos omega, or yeah, yeah. Option C. Yeah, now most of you could answer on this stage, right? So if you, this is square root of 4 into, this is just cos, this whole term, this is just cos square omega by 2. So your option is C. Okay. Yeah. You had to recall this definition. There is no way out of it. You are trying to write down the original signal as a summation of complex exponentials. Simple term, simple English. Okay. This is an infinite summation, but they only gave you two terms. Hey, can they make it AP, not AP typically, they can make it a GP easily, geometric progression. No, they can cook up variations. In this case, the way they simplified it is they made it a finite summation, just two terms in the sum. Okay, let's go to the next question. Block diagram of an ideal system and a real system with their impulse response are shown below. Auxiliary path is added to the delayed impulse for an unit impulse. Okay, there is an ideal system, ideal class, and then that online class with this online setup, right? This internet and all that, you have a delay. And also not necessarily the information that I say is somewhat corrupted. And also there is some additional modifications going on. That is what they have shown here. For a unit impulse input, this is input as impulse. The gain B is chosen such that y of 40 is same for both systems. What they are given here is y of 40 happens to be y of 40 for the ideal and the real system. For the ideal and the real system. First question, what is y of t? I think we learned some of this in control systems, right? X of s, h of s. The time domain, in fact, y of s, h of s. There is a product in the frequency domain. In the time domain, this is a convolution. This by definition is your output. Okay. Typically your output by definition y of t in the time domain, this is convolution of input and impulse response. Is a frequency domain that's in the time. Convolution became a product that we have seen so far. We also need to know, let me quickly recall few other transforms. Your delta of t transforms to 1. Okay. So if you look at your y, impulse, that is when your input is delta of t. This happens to be h of s. This is when x of s is 1. into 1. Okay, that 1 I am not writing explicitly. You could also see that in this side, you have your y of t. It's basically the impulse output, y impulse as a function. If you apply an impulse input, your output is just x of t, right? This is just inverse Laplace or inverse, inverse Laplace or Fourier inverse Laplace transform. Your things. When does this happen? By definition, this is when your this h, sorry, mm, your x of t happens to be delta of t. That is for an impulse. Okay, sudden sneeze in the class. How does that get recorded in the audio, right? Okay. Yeah, this is something that we already seen this. Kind of recall this. This is also, I think this is a third time or something like that we are coming across this relation. Even somewhere in electrical circuits or something like that, I remember this thing showed up. Right. So third time this concept, this specific concept is showing up. So this happens to be, now the impulse is just going to be h1 of t. And this is going to be, let me write that relation specifically here, okay? To know that y impulse of t happens to be h of t. I just showed this, not as your y of s happens to be of your impulse happens to be h of s. Yeah, this showed up in the 2024 paper, I think. Okay. So your h1 of t, h1 of 4t happens to be HAU of 4t. H1 of 4t equals H. H1, that is a combination. There is a summer there. So you have H1 of 4t. You have to be careful. This is H1 of the ideal, H1 of the real. Okay. So H1 of the real, because that H1 and this H1 are different. Okay. This is a real system, right? That is different from the ideal system. So H1 of 4t, that is summation with HAU of 4t. Now this equation becomes e power minus alpha times 4t, okay, u of t, that is h1 of 4t. That happens to be, and if you want me to color code it, let me write this in blue and green, okay. This is h1 ideal, this h1 real, h1 ideal is e power minus alpha into 4t. U of t. This is your h1 ideal. That happens to be equal to h1 real plus HAU. There is an auxiliary thing. That is e power minus alpha. Wherever there is t, put 4t. 4t minus t. U of t. U of t is a step. I'm not going to get into details of that. That plus beta u of t minus u of 4t minus 5t. So I know. So the student who did this question in this 2022 paper got All India rank 1. That is the kind of edge that I am talking about. So the edge in signals and systems, right? The weightage is very high. Edge is not necessarily to clear the exam. Perhaps for IN students, it helps to clear the exam. But the edge that you can get by answering any of these questions, they look hard, but if you answer them, I think the student who answered this got All India rank 1. Okay, 2022 paper. So this is the case. This is what they have given in the question. Now, can you simplify it? Many of this is going to go to 0. Okay. Now, you also have U of 40. Time is 4. Okay. So the step function, if the input is positive, this is positive. That's all you need to know. Okay. With that, you can technically answer this. If your input is positive, output is positive. This happens to be 40. This also happens to be 40 minus D, that is minus D. Okay. The input is positive here, that happens to be 1. The input is positive here, that happens to be 1. This happens to be 1. This is 0. Okay. U of positive input equals 1. U of negative input equals 0, which is what I'm using here. That's fairly simple. So this term happens to be 1. This term is 1. This term is 1. This term is 1. That last term is 0. For clarity, I'm going to erase that. Okay. Now, can you simplify this and tell me what the option is? So the U's kind of disappear. In fact, because this is in a recorded format, I can also substitute the values there. This into 1, input is positive, input is positive, input is positive, input is negative. Can you answer at this stage? You have to solve for beta. Yeah, I didn't separate beta. This is fairly easy now. This is minus 3 alpha t. Can take this to this side and simplify it. Beta is just this term. Beta is happens to be this term. Even the ones you can kind of forget. Yeah, 1 minus 0 is 1. Even that you can kind of forget. So your beta is that. Can you simplify that? And the step function while I'm waiting for an answer. Let's also draw the step. This is your u of t. This is your u of t. Wherever things are positive, its value is 1. Wherever things are negative, its value is 0. Let's also, if you want me to simplify this happens to be 3t e power minus 3t. You can take it to that side. You can pull it out common. What will be left out with this 1 minus e power minus 4t. So your beta equals alpha into 3t. If you pull out that minus e power alpha into 3t, you'll be getting if you pull out this term minus e power minus alpha t. Okay, so that's option C. So bottom line, hey, what is the step? I made it fairly easy for you. If the input is positive, say e power minus 4t, sometimes it's very confusing. Input is positive, output is 1. Input is negative, output is 0. Okay, and that is point number 1. Point number 2, they are always asking for impulse response. Impulse response happens to be the transfer function. Okay, now we are already starting to learn this. This diagram is fairly easy. There is a summation here. This signal gets added to the signal, right? This signal goes in, it gets acted by a gain or a transferred by this signal, this function, you get the output, right? We are starting to read this diagrams, right? So which is what is given here. You have a GP question. Your y of z, this is in fact an infinite tab FAR. Yeah, I'll come to that. What is this infinite tab FAR? I'll quickly answer that. But if you have to read this figure again, they are trying to confuse you. This is fairly straightforward. If you take x of z, if you multiply by z inverse, if you multiply by a gain of alpha square, you add it to the summation that gives you y of z. Your y of z happens to be x directly goes there. It's added to that. Then x has some change and gets added to it. Okay. Again, for clarity, what shows up here is x z inverse that shows up at this junction that gets fed up with the gain of this. So what shows up at this junction is x z inverse acted upon by a gain. We can also read that. X z inverse I have to make it that is x z inverse acted upon by a gain. That is what shows up here. And we can color code this. This is multi-channel, right? A square. That gets added to y. We can start doing the same thing. The value that we read here, whatever comes here, that gets multiplied by power minus 1. So what here is x z power minus 3. Right? That goes in and then we have the gain. So if you take the yellow arrow, right, that gets added to y again. So that is x z power minus 2 acted upon by alpha power 4. And finally, this also gets acted to 4. Dot dot dot. This is just an infinite GP. You can easily write it down, right? So notice your a by x happens to be h. Okay, that by definition is 1 by 1 minus r, where your r is this term. So this is 1 by 1 minus r, that is 1 by 1 minus z inverse alpha square. That happens to be this. You can easily compare and fill up the things. Okay, let me write this slightly clearly. 1 minus z inverse alpha square. You can quickly see that your alpha square happens to be this value. This function is same as this function. So your alpha square is 0.5. That is 1 by 2. Alpha is 1 by 2. This is an infinite GP problem, okay? So I already said they have to, there are infinite summations. They have to make it finite, simplify things. One example is, yeah, this. They gave only two non-zero terms in the infinite summation. Another way to simplify this is typically give an infinite summation that's a GP. Fairly easy to do. Okay. Okay. Now, what is left? Actually, what is left is fairly hard questions. Okay. An input x of t is applied, and notice the spectrum of that amplitude and phase information of the transfer function is given. So this is a hard problem because you are expected to convert a figure to equation. Given equation, multiplying, manipulating things itself is fairly hard, as we saw, uh, as we saw in this question. Given equation, manipulating and slightly gets over the head, right? Now this is a figure. From that, you have to extract the equation. In the sense, it is fairly hard. But if information is given in figure format, if you recognize that, this is fairly easy. Okay. The amount of prior knowledge required is fairly quite a lot. I have actually a playlist on biomedical signal processing. You can take a look at that playlist. 5-minute chunk videos starting from scratch, starting from basic complex numbers, complex variables. There are about 20-25 videos in that. It goes till this problem. Okay. So that cannot be explained here. So two things. I have a playlist on biomedical signal processing where towards the end I discuss this specific problem. You need so much prior knowledge for that. Signal processing, biomedical signal processing filters. Okay. Filters. This particular question, during practice, what are you supposed to do? Hey, can you do like shadow boxing, right? Can you cook up easy versions, hard versions, something like that? So I have also an important gate tip based on that question. One specific video. If possible, I'll try to add the links in the description. Okay. Gate tip video based on this question, where I also discuss a solution for that. I done that separately. You don't have to go to 2022 solution, try to find that video. I kind of done that separately. So I'm not going to repeat that. Okay. But this is hard. If you can kind of understand your h of j omega is j omega minus a, j omega plus a. If you can kind of invert this magically, okay, then you can fairly easily solve. Notice that omega of 10 power 4, you get minus 90 degrees. So angle is minus 90 degrees. You can easily solve for a. Then once you solve for a, you can write, quickly notice the amplitude of this is 1. And there's also a decreasing phase. That's why I chose this form, okay, which is fairly involved. But with this pointer, let me stop, okay. Yeah, but this question is fairly easy, so I'm going to do that. A block diagram of a two tap high pass. Let's write down what is y. Take x, gain of beta 1, give it to y. Take x, multiply by z inverse, gain of beta naught, give it to y. Add it to y. This is your x. So your transfer function is a function of z, y by x, that happens to be beta 1 plus z inverse beta naught. So given this, can you find out what is the value of the coefficient? Given some information on that, you are given the maximum and you're given some information on this. A ratio of maximum to minimum of h of z is 2, and then h of z max is 1. There are a couple of ways to solve this, but my preferred way is this. Okay. So here you have to find out what is h of z. What is the maximum value? What is the minimum value? What is the minimum of this amplitude? You have to find that. Okay. So you're given a complex function, you have to find instead of a simple real function, you are given a complex function. Can you find the maximum or minimum of that? That's what they are asking you. And h of z, z is confined to mod 1. Okay. Here, when you're talking about this z transform, you're confined to mod z equals 1. You're confined to the unit circle. In the z domain, z is a complex number. You're only allowed, you can only consider probable z values are only where mod z is 1. Okay, that is something, let me tell you. Okay, so how do you find this? Finding this is fairly easy. For that reason, I'm going to do this. Okay, but before that, your y is a function of, or y by x, your h of z, there are two terms here, term 1, term 2, right? Which is one they are referring to as a two tap filter. What is high pass? There is, little more, two tap, there are two terms here. Okay. Your y, this is some function of x of z, z inverse and all that. Whenever things are in this form, we refer to that as finite FIR filter. Okay. In fact, this is slightly easier to see in terms of uh, the discrete version. So I'm going to, so y depends on only values of x. Y doesn't depend on its past value. Okay. So this is an FIR filter, and there we have seen two things. One is two tap so far. We also seen infinite tap. This example. Your yz, there are infinite terms. It's a function of x and z inverse. There are infinite terms. So it's only a function of x. So it's FIR. And there are infinite terms here. So this is infinite tap. Okay. And then we have something called IIR, where y also shows up inside this function. The simplest example that I have in the PVQs is this. Your current value of yn depends on past value of yn and xn. Had it just depends on xn, input, sorry, output depends on input. At this stage, okay, this is just a simple finite impulse response. The moment output depends on past values of output, it's an infinite impulse response. Okay, your H is infinite. In fact, what is given here is an example of an IIR. Just from classification perspective, notice Y current value depends on past values of Y, the output itself. What you have here is an infinite impulse response system. Your H of n will not be finite, won't be truncated. There will be infinite number of terms here. Okay. Quick detail on that and also reading that question. So yeah, quickly, here output depends on past, present and past values of x. Past and present values of x. Here, your output depends on past values of output. What is your past performance? Your performance depends on your past performance, not just on your preparation. Okay. What you have done in the past, what you have done, your prior knowledge, your talent, your capability, your ability, right? All of that matters. That is supposed to be referred to as IIR. OP depends on past values of output. And of course, and past and present values of input and X. Okay. In this case, this is a output depends on output. This is at least what it means is H of t is not truncated. H of t or H of n is not, finite. It kind of like there can be an infinite series. Okay. Small terminology here. And okay, let's get back to this. How do you find this H of z? Can anyone say what the triangle inequality is? Because I don't have IN students, let's also make sure there are some students. Yeah, there are some students. Does anyone remember the triangle inequality? In this using, first derivative, second derivative, typically as you go to graduate school, they become absolute ways of doing maximum minimum. Start doing inequalities, start dealing with inequalities. And one of the most basic inequality is this triangle inequality. Length of a side will always be less than or equal to summation of the individual sides. You can, mod of this. You can think of a triangle, any one side length is going to be less than or equal to summation of the length of other two sides, right? For any vector, of course, this can be complex, this can be a vector, right? You have this inequality. There is also a corollary there. You can also take this length, subtract this length. This can be positive or negative. So for that reason, we can take one more absolute value of this that has to be less than this. Okay, this is a corollary, and this is your main inequality. So you know vectors, complex numbers. You can put a complex number variable there. This inequality still holds good. Okay. The reason to bring this is often so given two complex numbers, complex variables, or two vectors, the summation is bounded by this term. So you can actually identify this as the maximum. You can recognize, you can read it that as, if you take u plus v, the maximum value of u plus v is the maximum value of this. It is bounded by this value. It's a maximum value. You can read this as the minimum value of u plus v. What is the minimum value of this sum? Each term can be positive, negative. It's a vector actually. Positive, negative, has positive amplitude, negative amplitude. Phases are all there, but this inequality still holds good. So this is very important, especially as you go to graduate school. Okay. So for that reason, this problem, I like solving it in that sense, using that inequality. Okay. So if I had to write that, your beta 1 plus z inverse beta naught, the amplitude of this should be is bounded in the top by modulus of beta 1 plus z inverse beta naught. It's not visible. Let's give it a little more space. Modulus of beta 1 plus, I already said mod z is 1, so this is beta naught. Notice mod z is 1, mod z inverse is 1. So this term is 1. I didn't write that. If you're watching this video, if you're like skipping fast forwarding, or you're not listening to the description, right? You're typically missing a detail like this. There are comments like, sir, even if it's a simple formula, can you give? I try to actually give everything, but often, you know, someone is not spending at least the time that I spend making this video, right? They're going to miss information on that. It boils down to that. Okay. So this is bounded by this value. This is the maximum value. This is, we can see this as the maximum, and on the lower side, this again is going to be bounded by modulus of this minus, the modulus is somewhat irritating or confusing. Okay. You take the individual moduluses, this minus this. Again, z inverse is modulus of that is 1. So I'm just going to put a beta naught here. So what? Now that we have come here, okay. So I know the maximum value, I know the minimum value. So what? So this is H max and this is H min. So what? Can we verify if the given information, given option satisfy the given information? The maximum value is 1. So if I add the amplitude of the two numbers, it has to be 1. The amplitude of these two is 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 1. All the four options satisfy that. So the ratio of maximum by minimum. If you want, you can put this. This is given to be 2. This is given to be 2. Okay. So that in given terms, this is supposed to be 1 by 0.5. This is supposed to be 1. Numerator is 1. Denominator is 0.5. Then only you'll get 2. So which of the options the denominator is 0.5? Can we verify that? So going by maxima, all four make sense. Going by the denominator, can we verify one of the options? Only one of the options will work. Plus 0.6 minus 0.4, that is 0.2. You are not getting a 0.4. That is incorrect. This, you are not getting a 0.5 here. You are not getting a 0.5 here. You are only getting a 0.5 here. 0.75 minus 0.25. You get a 0.5. Only this option satisfies. That's the correct answer. Yeah. Yeah. Okay, so before my flow gets unbearable, okay, it doesn't get unbearable, but we have to, let's proceed. Okay, so this, if you ask me, this is fairly important, not just for gate, but even in grad school, this is fairly important. And this way of doing maximum, minimal, upper bound, lower bound, quite useful. You can go a lot farther than what you can do with derivatives and functions. If you look at this question, okay, it's a constant discrete system, the input depends on past values, sorry, the output depends on past values of output and current value of input. This is IIR, okay? And just that term suggests them as infinite number of non-zero samples in the impulse response. It's an IIR response or IIR filter, infinite impulse response, okay? So for that reason, option C is correct. This term looks like R. Y of n equals whatever my past is, I'm going to subdue that, right? Give weightage less than 1. Your R is 1. If you do it a couple of steps, you're going to get an infinite, your y n plus 1 will depend on both the y n minus 1. Y n plus 10 will depend on previous values, right? So, or, this, notice, this is going to be 0.5 square into y n minus 1. Can go on and on like this. So every time the effect of the past output, specifically the y n minus 1, the term kind of decays. This is a fraction. And the fraction gets smaller and smaller. So as far as your x is nice, your output is nice. That is what this means. As far as your x is nice, your output is also nice. Here I'm making use that this r is less than 1, mod r is less than 1. If that number is, absolute value of the number is greater than 1, of course I have an y kind of blows up, output blows up. 10 power 2, 10 power 100 is quickly, 100 steps, you are like, this value kind of grew grew a lot. Unless it's like you are investing and, uh, you want to grow your portfolio, right? You don't want R to be greater than 1. Typically, that's the only case where you want R to be greater than 1. Real world scenario. Most real world scenarios, you want a stable system, right? Okay, and then hey, this is fairly nice. Okay, reasonably nice system. This is this is this minus is a very problematic term. It's non-causal. This is non-causal. So fairly nice system. You have a non-causal impulse. That's a red flag. Okay. Non-causal impulse output for a good system doesn't happen. For that reason, I am ruling this one out. And I already said it's not infinite. It's not finite. It's infinite. So I also ruled that one out. Okay. I try to use some common sense justify this, but anything beyond that is going to be fairly hard. Okay. H of S is given. Can you find H of C? It boils down to recall. Okay. This is not something that you expect to recall. How do you go from H of S to H of Z? For example, H of S to H of J omega, just substitute S is J omega, you can do this. But how do you go from S to Z? S domain to Z domain. This is fairly easy. Does anyone remember that bilinear transform? You have to substitute your, in place of S, okay, you have to substitute, oh, this is 2 by T. Does anyone remember this? How to recall this? Okay. So wherever there is this, substitute Z, Z minus 1, Z plus 1. In place of F, substitute this. Okay. And you have to recall this. Recall the definition of bilinear transform. Okay. H of C. I have already solved this in the 2021 solution. So at least let me tell you. So by substituting, notice your H of Z is going to be 1 plus, in place of S, I'm going to put 2 by T. There is also a 10 power 6 into, so if I write it this way, you get confused. So let me write the 10 power 6 here. 10 power 6 and then Z minus 1 by Z plus 1. So that yes, I kind of replaced. This whole term is the yes. There is one more yes in the denominator. That is again 2 by T. Z minus 1. Z plus 1. You have to find the pole of this, which I said, wherever the denominator, roots of the denominator or the poles of this, wherever this function is singular, that's a pole of this, you can quickly solve at the stage. And T, this is sampling rate is 100 megahertz. Fs is 100 megahertz. So your 1 over T is Fs. That is 100 into 10 power 6. Okay. Now find the pole of this. You can do that. So question like this. So let's say I couldn't kind of recall the substitution. This is a typical scenario. Okay. For biomedical students, this is a typical scenario. No, I'm not explaining this question again. So this is how do you go from H of S to H of Z? Wherever there is S, you have to put instead of S, replace this. And then find out where this denominator, roots of this denominator. Okay, there is no explanation. In place of S, substitute this expression of Z. So notice, in place of S, I substituted that expression of Z. And then find the where the roots of the denominator, that is the poles, the singular functions. Okay. I kind of discussed this in control system PYQ discussion, right? So I'm not going to, there isn't more to explain here. But let's say you couldn't recall this. So again, there is one more thing. What is the poles of this? Let me also write that down now. Write that one down. So poles are zeros of poles are roots of denominator. If denominator, it's a root of denominator, denominator goes to 0, the function goes to infinity. Singularities of h of z. Okay, poles are roots of denominator. So you have to do that. Okay, 2-3 steps down the line, you will actually get it. It's not actually you can see what the root is here. Okay, if you ask me, I can quickly say that this is going to be the root of the denominator. The z plus 1 will get cancelled. Whatever is there in the zeros of this function, I don't care. Notice I can quickly read that function, that z minus 1, I know it's the root of the denominator. If you substitute z is 1, the whole function goes to infinity. Substitute z is 1, this term is 0. Whatever is there in the numerator, that by 0, okay, you're getting infinity. H of z is infinity, right? At this stage, I can answer this without any further simplifications. Point number 1. Okay. What? Okay. Someone asked this. Hey, at least did you follow this? Someone had a question. Can you explain this again? Wherever there is a substitute this expression. That is by definition the bilinear transform. Okay. This by definition is a bilinear transform. Or getting bilinear, h of z from h of s. That is a definition bilinear transform. Did you get this? Point number 1. Instead of s, put this function of z, whatever I have written. Substitute this for in place of yes, which is what I did. Okay, and you have to recall what to substitute. That is from recall memory. Okay, that is a definition of bilinear transform. What is the pole of h of z? Where does the denominator go to 0? I know it goes to 0 when z is 1. So I know the answer is 1 at this stage. The poles are 1. I answered it. The worst case scenario, let's say you don't know this. You couldn't recall this. Okay, you don't know this function, so there is no way you can read that pole. Told you, any unknown NATs towards the end of the examination, you are going to guess 0 or 1. Okay. If it's a, if it's a, if it's a, even I had some suggestions, right? Typical core subject numerical NAT type question, I'm going to guess a 1. Mathematics NATs, complicated signals and systems NATs and all that, I'm going to guess a 0. Just in case I know this, I don't know the answer, but NAT is no negative marks. I have to fill up something. In this case, let's say if I couldn't recall what I would have guessed is very, very close, I would have guessed 0, going my rule of thumb. Had you guessed 1, you could have, in fact, for this question, you could have got the answer. Okay. Towards the exam, answer all any days. That is the bottom line. But here, make the substitution in place of yes, substitute this, and whereas a big function becomes singularity, that's your answer. It becomes a singularity when z is 1, so that's your answer. Okay. If I were to guess, I would be guessing this. Okay. In fact, I would have guessed 0. I wouldn't have got marks, but happens. Even if you get 1 or 2 questions correct just by guessing, NET is correct by guessing, right? That means a lot. Okay. What is left is this continuous convolution. I told you this is, again, I have done that integral in the GATE BM 2020 solution. I'm not going to do that. Okay. And, this is a fairly hard question, but if you know Fourier transform and all that, this is a sinc function and the spectrum is getting shifted, right? So the rectangle is getting shifted. The amplitude of the rectangle remains 10. So I'll get, I guess, a 10 here. Okay. But this is fairly hard if you have to do it systematically. You have to recall many, many things. For that reason, I'm also going to skip this. Okay. But the solution is there in 2021 paper. Solution, all properties of Fourier transform that you need. Finally, there is one question left. Okay. What is the cross correlation? I'll do this and we'll wind up. Can you tell me in the sequence? So the answer key is this. I think when I discuss the solution of 2022, I gave this. Okay. But I think the correct answer is only this. Okay. We'll get that today. But can someone tell me this? What is the sequence x of n? Okay. What is this sequence? What is the sequence y of n? Again, information is given in the figure. Can you read that information? There are like 8 points, right? Can you quickly tell me what those 8 points are? If you need space, one question can benefit by having some space for your x of n, y of n. So we are going to have trouble. We cannot just even read the values from the figure. Just tell me two, three values. No, not for entire values. Not the 8 values. Okay, someone gave me the values. Thanks. So this is, in fact, um, let me write it. I need space. Okay, let me write it this way. You start at 1, then there is 1 by root 2, then there is 0, then there is minus 1 by root 2, then there is minus 1, there is minus 1 by root 2, there is 0, you end at 1 by root 2 is your x of n. Your y of n, and this happens to be, first value is 1 by root 2, second value is 0, third value is minus 1 by root 2, fourth value is minus 1, fifth value minus 1 by root 2, sixth is 0, seventh is 1 by root 2, eighth is 1. Okay. Let's find out what is y of minus n. That is, you write the sequence in reverse order. Last value is 1. Then I got 1 by root 2. Then I got a 0. Then I got minus 1 by root 2. Then I got a minus 1. Then I got minus 1 by root 2. Then I got a 0. Then I got a 1 by root 2. This is the original sequence in reverse. At this stage, okay, they have cooked up a problem. Point number 1. They have actually noticed your x of n happens to be x of y of minus n. There is the symmetry between these two functions. Okay. recognizing that, you can quickly answer this question. Okay, this is how they have cooked up, I suppose. Method number one. But method number two, okay, the way you would do convolution and correlation would be slightly different. You have to make one difference. Okay. And let me explain that difference over there. What I'm going to write down is your xn at the top. Okay. And for finding convolution, we are writing yn here. Okay. But what for finding cross correlation? So this is for convolution, you'll be writing the values of yn. For finding cross correlation, you have to write down the values of yn minus n. This has to do with the definition of cross correlation. Again, it's fairly easy to do in the stable format. So let's write down what is y minus n. Okay. I'm going to write down x n there and y minus n. Where xn happens to be 1 by root 2. Let's say that's root 2. 0 minus 1 by root 2 minus 1 minus 1 by root 2 0 1 by root 2. Your yn happens to be y minus n happens to be, I'm writing this in the reverse order, 1 by root 2 0 minus 1 by root 2 minus 1 minus 1 by root 2 0 1 by root 2. I hope what I have here is same as, yeah, I have minus 1. Okay, what they want is r x y, the zeroth element. Okay, in terms of cross correlation, okay, convolution, you are only getting positive indices values, right? Depending on if the functions are causal, signals are causal, this is what you're getting. Here you will be getting signals for the negative indices also. This is a complication that I did not want to get in earlier. And how you read this value in this table is this diagonal. That summation of that diagonal over there. For example, this and all is immaterial. I'm not going to fill it up. I'm only going to focus on the diagonal elements over there. I have 1 by root 2 here. Okay. This into 0 will be this 0. Let me have some guidelines. Okay, this is somewhat messy, but this is what your rough sheet. You don't have a gridded rough paper, so this is how it's going to look like. Second value, third value goes till here. Goes till here. Value goes till here. Fourth value goes till here. Fifth value goes till here. Sixth value goes till here. Seventh value goes till here. Eighth value goes here. Okay. And those values would be 0 times this again as a 0. Minus 1 by root 2 times minus 1. That is 1 by root 2. Okay. Minus 1 times this is also 1 by root 2. Okay. Minus 1 times 0. That is a 0. 0 times this. This is a 0. And finally, I have 1 by root 2. What is the summation of all of this? So the summation of all of this is 4 times root 2. that happens to be. Again, okay, what I'm getting here is again 2 root 2. I'm getting back to 2 root 2. Okay, what I will do is, again, see, the last time I did, I got this as the answer. This was the official key. Okay, this is the key, and this is what I getting. I'll better do this in a computer. Okay, I'll use cross correlation function for two signals. I'll find out, and I'll let you know this. I'll just put that updated value. You know, I keep getting A, but for some reason this answer key is B. I'll give you 30 seconds. Is there any mistake in what I have written xn and y of minus n? Yn in reverse order, xn in the same order? Are there any mistakes there? Even when I did it this way, I was getting a root 2. No issues, right? Okay. So I'll decide based on, computer output. Let's just leave it at that. Either, it's either objectively A that I keep getting, or this is, as the answer key says, this is 1 by 2 root 2. I try to keep giving uh, some benefit of doubt to the committee, but whichever method I use, I keep ending up at option A. Okay. But anyways, see, this is the reason I also did this cross correlation towards the end. This is if it shows up in the exam, okay, this is something that I wouldn't waste time on. Certainly at the first half of the paper. But if discrete correlation shows up, this is one of the easiest questions that you can answer, and which almost every year there is a question on that. Okay, some form or the other. So at least make sure biomedical students you can attend distinct convolution questions. Either do it as number of likes in social media, or the table that I wrote down here. Okay, do it at the table. Okay, so that brings us to the end of even S&S discussion. We are also over time. I am kind of like I don't think I can sit for a few more minutes. Let's wrap this up in a minute or so. What you don't want to do is to miss that edge. Okay, biomedical students, IN students, you're supposed to be good at this. The more marks you grab, you can retain your edge. Biomedical students, if you at least learn the basics of whatever I taught, okay, you can get 3-4 answerable questions. This, along with controls, there are about 7 questions. Okay, about 12 to 13 marks. So you can grab about 8 marks fairly easily. Okay, and that was the objective of this session.